Hello guys, this is TurboMind here. We are going through the first example of OpenMDAO and we are trying to understand how OpenMDAO represents variables and to solve a simple numerical model. A nonlinear equation to solve is provided here, and trying to assign solvers which are implemented inside the OpenMDAO, and we're trying to get to know OpenMDAO a bit better. Now this is the official documentation of the OpenMDAO's developer team, and how to get access to this one. It's just simply openmdao.org and documentation of OpenMDAO latest, and we are here. And into getting started, it's going to tell you how to install that. It's pretty simple, thank God. It's not as difficult as the PyOpt sparse or AdFlow. You're just going to have to write pip install OpenMDAO, or you can also use the package here, manage packages, and just search OpenMDAO and it's going to pop up here. I'm using PyCharm right now, and whatever IDE you are using, you can also install from that as well. Now we are trying to understand how these things work. Into the basic user guide, how OpenMDAO represents variables. There are three types of components: the implicit variable component, the explicit component, which is just easily you are defining the output equals input times whatever, just like this one. So it is an explicit expression. And then we have the implicit component, which is a bit trickier, like this one. This is some sort of nonlinear equation. It's not solving z, for example, from y simply as that. If you substitute z into this equation, you are going to have a nonlinear equation which looks like this: z equals sine of y. Substituted inside of that, it's going to be an equation which x is the input, and it's going to solve for y. So this is a nonlinear equation. You're not going to explicitly solve it. So you need to define you need to assign some solvers to it, and OpenMDAO already has a bunch of them, and it's going to change the values of y to make this equation work. Then we are going to define the variables here that OpenMDAO is just telling us how to do them. And let's get to it. We are trying to solve this equation and see the answer inside the OpenMDAO. So I'm going to go to my IDE, and I'm just trying to import OpenMDAO.api as OM, and then we will need NumPy. And so the first thing would be the x. The x is an independent variable component. Why? Because it's an input that we are providing it. It's independent. The values of y and z does not affect x. So x is an independent variable component. I'm just going to try to define it like that. And you can see it's the output of this component. Okay, so it's not going to be anything strange about it. So when you're trying to work your way into the OpenMDAO, you're going to work with classes, you're going to work with methods, attributions, inheritance, and it's best if you would be acquainted with them and know what they are. So to define our x, I'm gonna say, let's say, for example, x, okay, which is OpenMDAO dot independent variable component. So it has inherited the independent variable component of the OpenMDAO, and it's going to use its attributions, its methods, and all of its capabilities. How we're going to do is First things first, we're gonna make a setup, okay? And we're gonna add the input or output of a component like this. We'll go self.add output, and it is the X, okay? That's it. For this one, it's done. It's not going to calculate any sort of equations, whatever. So this one was just pretty straightforward. Now, the second one is going to be implicit component, explicit components. And how do we solve this? How do we define this? We have defined X so far. Right now, we are going to define these two. Let's do this with the easier one. Z equals sine of y and is an explicit component. It takes y as an input, gives z as an output, and it is an explicit component. I'm going to name this one equation 2 for myself, and I'm trying to define it firsthand, and it would be like this. Equation, whatever name you are giving it, equation 2, for example. So, and it is an explicit component, okay? Explicit component of OpenMDAO, and it has some set of functions, method, and inside the setup method, you are going to define inputs and outputs. And the input is going to be self.add input. The input is y, as you've seen before, and the output is z, just as easy as that. And we are using quotations to define the names of our inputs and outputs. And the next thing, we can define the setup partial. This is gonna declare and calculate the partials, so in case we need the derivatives of our variables. So the easiest way to do that is we're going to go say, get me the partial of everything with respect to everything, and method is going to be finite difference. Yeah, that's it. This is going to provide it's going to estimate the derivatives, the partials, with finite difference method, and provide them automatically to, let's say, optimizers or solvers that need derivatives of your variables, like SLS cubic gradient based optimization. And then we are going to compute our z here, which is sine of y. So we're going to do it inside method compute. Yeah, just like that. And it's not going to be like that. It's going to be self, it's going to have inputs, it's going to have outputs, it's going to have, just to look like the definition of the method, key arguments. And so we had y. We define it like this: inputs of y, inputs brackets y. This means that from the inputs, take this y, okay, and I'm assigning it to this internal variable of y. And then the outputs, I'm going to write my equations now. The outputs of z, let's go, equals numpy dot sine of, let's say our inputs is going to be in degrees, not radians. So I'm going to use numpy degree to radians of y. Okay, just like that. Numpy degree to radians of y. There's going to be z equals sine of y in degrees for y. Now, this is finished. This one is just done, and we can now go through the next one. Now, this bigger equation here, which is an implicit one, we are going to define this. And this is going to be the equation 1. equation 1 is a class. We define our components like this. Equation 1, which is an implicit component. Okay. So we are going to have our setup. It's going to have its input. Now, this one, y could be as an output because it's going to solve for y. Okay. As it is tricky, it looks like an input as well. But the thing is that y is an output, and x and z are the inputs. So x is the input, obviously, and z, which is appearing here, is going to be an input. So we're going to define them as well. Add input of x, add input of z, and output. And these are going to be signed like this. This is going to be z. And no, sorry, I'm sorry. These are going to be not defined here. See, I just made a mistake. We are just trying to define them right now. And add output of y. We're just setting up. We're not doing any calculations here. Now, the thing is, we can assign a nonlinear solver right here to our class of equation 1. This component can have a solver internally. So you can use self dot let's say nonlinear solver OM dot nonlinear block of Gauss-Seidel, or let's say Newton solver, right? And we can assign a linear solver as well. Dot, let's say direct solver. So we can internally just assign solvers to our component and ask it to solve. Now I'm going to comment these because we're not going to need them for now. For this example, and the setup is complete. We would now define a set of partials. We might not need them, but it won't hurt to define them here. So it's going to be declare partials and of what? Of everything with respect to everything, and method is going to be finite difference. The thing is, you can define analytical derivatives yourself here. So, and it's going to be enormously efficient for your optimization workflows. But for now, we're just defining them with the finite difference. We are approximating. Now, in order to solve a nonlinear equation like this, which will eventually look like this, as you can see, this is a nonlinear equation. We're going to define nonlinear solvers and apply nonlinear method to our implicit component here in order to solve it correctly. We're going to go apply nonlinear, okay? And it's going to have, these are redundant, inputs, outputs, and residuals, okay? Inputs, outputs, and the residuals. And then we can, to avoid this sort of warning here to look like its own definition with key arguments as well, and we're going to give it the x equals, it's look like the compute part which we had here. We're going to have our inputs and outputs, but with a tiny change. So x is the inputs that we had, y is the inputs that we had, and y is the output. y is the output of this equation. As you can see here, y is going to be our output because it's going to solve for y and give us the value of y. And x and z are the inputs. As we saw earlier in the equation, the input is going to be z just like this. Yeah. And in order to define our equation, our nonlinear equation solve, we are going to, let's say if we wrote that 0 equals, this is going to be wrong, okay, by the way. Numpy that cosine, just like this one, cosine of xy minus z times y, cosine of numpy the degree to radians of x times y, and minus z times y. So what is the problem with that? It's not going to work like that. You're not going to put 0 in there. Instead, you're going to define residuals of y. So this means that it's going to solve for y in order for this equation to be like that. This is it. We have defined our equation 1 as well, and now we have to group these two together and start an MDA, which is going to be a group, an OpenMDAO group. And it's going to have obviously its setup, and it's going to look like, it's going to have its subsystems instead of inputs, because the group that's going to contain some components, and it's going to have its subsystems. So one of the subsystems will be the equation 1, right, that we already defined, and it's going to be what was the name of that? Just like equation 1, I'm going to call it. And this promote thing is important. We are going to promote everything here. This means that all the variables that we defined inside equation 1, okay, which are going to be x, z, and y, are going to be promoted, are going to be out of the internal parts of the class, are going to be accessible globally among all the workflow, all the group of this OpenMDAO group that we have, and outside of this subsystem, they are going to be accessible. And we promote everything. We can promote them one by one. Let's say promote x, but it's going to be inside brackets if you're going to promote them separately. And but I think here it should be like that as well. It will be better. So next subsystem is going to be the equation 2. Yeah. And we're going to promote everything. And by the names being the same, see the x's in the equation 1, and the equation 2 we have y and z, and y and z in the equation here as well with the same names. OpenMDAO is going to automatically see that they have the same name, so they're going to be connected together. They are same variables that are used inside of different components. And we're going to assign our solvers here inside a group that contains 2 components, which one of them is explicit component, one of them is implicit component, and it's going to solve them. Okay, the equation 2, the nonlinear solver is going to solve the equation 1 and 2 together. We're going to go with Owen dot Newton solver, one of the most efficient. Now here we need to say that when we have assigned the nonlinear solver, solve subsystems was false or true. You can assign false or true. Okay, now internally there's no big deals to solve, so we're going to set it to false, but it's going to work with true as well. So, and the linear solver is going to be, let's say, direct solver. Direct solver is a linear solver. Now we have assigned both linear and nonlinear solvers to our MDA group that contains two subsystems. Each one is a component, which inside of it has some sort of inputs, outputs, partials, computings, nonlinear computations, and that's it. Now I've assigned them, so our workflow is done. Now I'm gonna go set up the problem. Sorry. Yeah. And we are going to have an OpenMDAO group, OpenMDAO problem. Okay, now that we have defined our MDA group, our components, we have assigned nonlinear and linear solvers, we need to set up our problem. So in OpenMDAO, we run things like this: prop equals OpenMDAO dot problem, and inside the prop we have a model which contains our MDA group, and we have prop dot setup. It's going to set up our problem, and now we're going to assign values, which will serve as initial values for our nonlinear equations. So it's going to prop dot set val x equals, let's say, 2, and y, for example, 4, and z to be like, for example, half, because z is a sign. Sorry, because z is a sign. It's going to have limited value. And note one more thing. I have modified this one. This was wrong initially. I had written apply linear, which is obviously wrong. You are applying a nonlinear method to solve your nonlinear equation. Okay, so this is apply nonlinear. Otherwise, it's going to throw errors at you. So after setting the values, we're going to have prop.run model. It's going to run and solve the whole thing, and we're going to have print x is going to be prop.getVal this time. It's going to be x, and then y, okay, and then z. It's going to give us the values. You can also access them like this. You go, I think, prop of z, if I don't make it with problems. So it's going to be prop.getVal, and let's run the model. Okay, that's it. Let's try that one. Let's try the other form of writing, accessing. I'm going to access prop to z like this, prop z. It also gives me the value. It also gives me, if I address it like prop of z, also prop.getVal. Okay, so this is gonna work just fine like that. And if we change the value to 1, it solves it. It's going to say that Newton solver has converged in 5 iterations. And our solved subsystems could be either true or false. Let's see the difference. If it doesn't make a difference, we don't need to solve the subsystem. So if we put it into false mode, if we don't have to put it in true, that's what I would do. This is it. The model's ran and found the values of our nonlinear equation for different values of x. X is the input, but y and z are just initial values. X is going to be the actual value because it's not going to be changed, it's independent. But these two other variables, are going to be changing. And this will serve as initial value. So that's our model has worked just fine, gave us the answers for the nonlinear equation. In the next videos, I'm gonna run this thing, double check the model by running the equations in EES, Engineering Equation Solver, and maybe Excel, and find if they give us the same value. Double check our model and learn how to solve nonlinear equations in Excel and in EES as well. So that's it with today's example. Please don't forget to like, share, and subscribe. And if you had any problems, any questions, please share them with me in the comments section, and I'll try to address them if I know the answer.